Every now and again, I see videos of people building computers in games like Minecraft or Factorio, and I'm just always completely blown away by what they're able to accomplish. But I also look at it and think, this is at such a high level, and I can't even begin to fathom how they do anything here. I mean, I don't know how a computer works. So, how do you even go about building something as incredible as these people do? And that first part bothered me. I don't know how a computer works, but how difficult is it actually? Like, how much does it take to build a working computer? Not a good one, but a working computer in a game like Minecraft. And I figured the best way to find out is to try it. And so I did. And so I built a working computer. This took me roughly 2 weeks of working in the evenings and on the weekend. And it's a fully functional, if very slow, computer that is, in theory, capable to do any sorts of instructions you program into it. It consists of an arithmetic logic unit and of some essential registers, RAM and instruction memory, a clock, and some method of addressing the instruction memory. It is capable of jumping, and that is pretty much it. It, as I said, took me 2 weeks. I did not start out knowing how a computer works, but I figured it out in building this. Obviously, I didn't rediscover computers from first principles. I did use the book that is associated with the NAND to Tetris course, called The Elements of Computing Systems, to tell me what I need to do on the big picture, what a computer should look like. I followed their design specifications. But as far as Minecraft goes, as far as Redstone goes, I did figure the vast majority of this out on my own. I refer to the wiki and Reddit post here and there in very few places. Most of it I experimented until I got it working and doing what I wanted to do. And I will go into great detail to the entire process, and I will explain the entirety of this by just explaining how I constructed it step by step. Because the big aim here is that I want to show that it is possible, starting out not knowing how computers work and knowing a thing or two about Redstone, but certainly not being an expert in it, being able to build a working computer. But I first, before I go into all these details, want to talk about what I learned in the process and what makes this so fascinating. All what I'm building up here is hardware. This part over there I can code, and I will talk about the code I've written and how I've written it and what it does. But this hardware, these are things which in an actual computer are hard-coded in the chips. And I, in just building this, really started to appreciate why things like clock speed in a computer come to be, how signal travel time can become an issue, and how a good architecture, a good construction, which is not this, since this is my first attempt, and also it's Minecraft, so everything is massive, how that depends on what operations you want to optimize and what a computer is supposed to do. And it matters how closely you have your memory to your CPU to be able to perform operations quickly because it takes time to grab information out of memory. All these concepts that people who built computers had to deal with for as long as computers have been around, I also started to run against in building this Minecraft computer. And what makes this fun is that it's not just a purely logical exercise in these are the operations that need to be performed in this situation that needs to happen. Building up all the logic was challenging and a big part of the process, but I also physically did build the computer. And I can watch the computer work. I can look at the wires. I can see which ones are active, which ones are not. I can see which data I'm currently reading, where I'm writing to, because I am building a computer in a 3D space that I can exist in and look at the actual processes. So the logic doesn't remain fully abstract. You can see how the logic interacts with the hardware, and you can understand by the end that all this you can forget about, and you only need to think about the actual code you want to write, what it wants to do. And this architecture here, all these redstone lines and pistons and repeaters and comparators will just interpret the operations and do what they're supposed to do. And by the end of the entire process, I still end up with very low level having to write machine code by hand, but I am much closer to interacting with the computer the way I would the actual computer. I am now telling the computer what it needs to do in an abstracted way, and actually doing it, actually performing all the operations, is just done by the hardware that I constructed earlier. And seeing how this comes together, how you start out from elemental building blocks, and by the end you are able to abstract to actual commands, and these commands are performed, and you can write code that performs mathematical operations that are not coded into the computer. That is very cool. So my big picture thing I want to say here with this project is I built a computer in Minecraft. And if you dedicate a bit of time to it, you can too. I am not a computer scientist. I'm not an engineer. I don't know these things. But reading up on them and trying, experimenting until it works, within a very reasonable time frame of maybe 25 hours or so, I managed to construct this. Now, right off the bat, I need to clarify something. When I say I'm not an engineer, I'm not a computer scientist, I mean it. I am no expert on how these things work, so my explanations will definitely be incomplete and some parts might be wrong. This is not the story of an expert telling you how things work. This is the story of how people can figure out how these things work. And I have this baseline understanding that computers are somehow built out of logic gates. I know, like, conceptually what a logic gate is. I don't know how they work. I don't understand the electrical engineering behind it, but I know what they do, right? You have an input signal and then you have an output signal. So in this case, my input is 0, the lever is off, and the output is 0, the lamp is off. And then I turn the input on and the output turns on. So this output is just identical to the input. That is very simple, very obvious. And taking that one step further is a NOT gate. So the output is always the opposite of the input. So this lever is off, and the way Minecraft works is redstone torches are on by default, so this lamp is on. But the second I send a signal into this block, it turns off the torch and the block turns off. Now, this is just about all you can do with a single input, but you can, of course, have multiple inputs. And this is when we get into logic gates in the way that I built them up here. Now, what I did is one Saturday, 3 weeks ago, I just sat down and decided, let me play around a bit. So I plonked down 2 levers, some redstone, and then I just used redstone components and figured out what happened if I combined things. And then I figured out what type of gate that would be. So the basic concept of a gate is that of a truth table. Now, this is something I do know from math courses, but basically I need to explain truth tables because they are fundamental to this. The question of what the output given certain inputs is that of mathematical logic. We can interpret each of these signals in the same way mathematical logic interprets statements. Now, a statement in a mathematical sense is either true or false. So I can say it is raining right now. And then if it's raining, the statement is true. If it's not raining, the statement is false. I am sure you can come up with many, many statements that are neither true or false, except no, you can't, because if it's neither true or false, it's not a statement, not in the sense of mathematical logic. It is true or false, which, of course, with computers and signals is represented by being on and off. So what these signals represent, what it means for this lever to be on, doesn't matter on the level of the gate. It matters on the higher level. What do I want to achieve with this logic gate? But it does not matter on the level of the gate. All that matters is, given certain inputs, what is the output? So here I have 2 inputs. I can call these X and Y. And these 2 inputs, of course, have 4 possible different states. So there is the state of both being off, and then the lamp is off. I turn X on, the lamp turns on. So now this state would be X1, Y0, output 1. I can turn just Y on. So now X0, Y1, output is still 0. And I can turn both on, the 4th possible state, and the output is still 0. So in terms of a truth table, what this would mean is the output is, for any given combination of inputs, always 0 except for the specific input of X being on and Y being off. So this is why you can call this X and not Y. So this is only on if X is on and Y is not on. And in terms of Minecraft, this is achieved with this comparator here. It is possible to build all of these gates exclusively out of redstone torches, but I did not do that. I used comparators in places. So for the purpose of understanding, I will explain all of these components step by step. So I want to build up a computer from the ground up. So I want to explain what the components that build that computer actually do. So a redstone comparator can take a signal from the bottom, from this side, and it outputs a signal to the top. And it can also take a signal from the side. Now this redstone comparator is currently set to subtraction mode, which you can see by this red lamp here. If I just right click it, I change it. This does not really matter too much because what this does is it subtracts signal strengths. And in Minecraft, if I have any sort of redstone signal, whether it comes from a torch or a level or something else, it starts out with a signal strength of 16. And every block it travels, the signal strength drops down, and at a certain point after 16 blocks, there will no longer be any signal. And if it goes around corners, it still just counts the amount of blocks. And here you see the signal is off. At this point it's off. And here, well, this obviously doesn't work. At this point it's off, here it's still on. But I am not working with signal strength. So in theory, signal strength, as you can see here, is some form of subtraction already with this comparator. I am not working with any of that. I am doing completely binary off or on logic. So in terms of this comparator, it will see that this input strength is higher than this input strength for the simple reason that this has a signal strength of 16 at this point, but then it travels one block, so it is in the input only an input strength of 15, and then this is directly connected with a repeater, and what a repeater does is it resets the signal strength back to its maximum. So this is how you can repeat a signal and send it as far as you want, but it also introduces a delay that is also toggleable. So continuing, this is an OR gate. It's one of many versions. The most simple version, I suppose, is to just plonk down two levers, and now if one of the two is on, this output will be on. What I'm doing here instead is I'm also adding repeaters, because one thing repeaters do is they only take an input from the bottom and an output at the top. They do not allow flow the other way through. So I suppose that's what a diode does. There are other ways to do this in Minecraft that are also used in this setup. One of the other ways is that you can use blocks like glass, because glass blocks have this fun property that they are transparent, and all transparent blocks in Minecraft allow a signal to travel up but not down. So this also only allows flow in one direction, as in only up, not down. So OR gate does what it says. If one or the other is on, the lamp is on, also if both are on. If X then Y, so there's some implication here. Right now, both signals are off. The reason this is glowing is only because, like for example, I could add a repeater here, then it doesn't travel back. So right now, neither are on, but because of this redstone torch inverting the signal, the output is on. If I turn on Y, the signal is also on. If I turn on X, the signal turns off because it turns off this redstone torch. But then if I turn on Y, the signal turns on again. So again, with the statement here, if X, then Y. If X is turned on, then Y toggles the lamp. If X is turned off, Y is always on. So this is the mathematical implication, which in terms of logic has this very fun interpretation that if your premise is wrong, it doesn't matter what else. Like the outcome will always be true if the premise is already wrong. But in terms of the gate, all it means is it requires X to be on for Y to matter, and if it's off, it's always on. Going forwards, this is a NAND gate. Now, NAND gates are really important. In theory, you could build an entire computer out of NAND gates, Wikipedia tells me. And what a NAND gate does is it's a sort of AND gate with an N before, so a negated AND gate. So it is a not AND gate. This lamp is on except if both inputs are on. So this inverts both inputs and then turns on the lamp. Next one is an AND gate. An AND gate does what it says, except this is not as simple as you might think in how it's constructed. It's not as simple as the OR gate, but the AND gate turns on if both input signals are on. In terms of how it's constructed, I once again use a comparator here. This one is not in subtract mode, but it would not matter for this, or rather for most purposes. It does not matter in how I use it, because now it just compares signal strength. The only reason I needed it in subtraction mode earlier was because this lever was one closer. Here the signal strength already dropped by 2, the signal strength dropped by 1. The signal from the side is stronger than this signal, so the output is off, which means X needs to be on to stop the signal being blocked, and Y needs to be on for there actually to be a signal. And then we take the NOR gate. The NOR gate is like an OR gate, except not. So it says neither can be allowed to be on if I want the outcome to be on. And now this is an XOR gate, and this is already much more complex. Indeed, this is a thing I gave up on, and I looked on the Minecraft wiki. The Minecraft wiki has all of, I don't know if they have exactly these, but they have all types of gates. I didn't use the wiki a lot, but I did use it for this XOR gate, which I never used in the actual computer. But this XOR gate, what it means is it is like an OR gate and that one or the other needs to be on, but it is exclusive, so if both are on, the signal turns off again. And that is already much more complex, and this is the implementation from the wiki using just redstone lamps. I plonked down some signs as to what is actually happening here because it wasn't super obvious. So this is a NAND gate up here, and it goes into this negation. And then I have on the side a negation into an OR gate, on both sides rather, and then a NAND gate here at the back. And this combination, and I could take the same logic with these gates I built over there, can build an XOR gate. So this was my initial just playing around stuff. This is my, I call it, it is the redstone testing world, and as you see, it is very empty because I don't do a lot of redstone testing. I played around with villages a bit, and I developed a sugarcane farm that doesn't require minecarts to collect your sugarcane, which is stupid because it loses half the sugarcane, but it's super cheap, so it's fun. But that's about all the stuff I designed in here. The only other thing I designed was a not properly working trenching machine for perimeter building. Most of the time I do engage in technical Minecraft, but I most of the time just use things other people have done. So this was really my foray into working with redstone. And this is where I stopped on that first day. And it is in this world where I just showed off these components that I actually built the computer. I sort of just built things step by step, and as I built the additional components, I just added them together and ended up with the computer in here. So the testing world turned into the world with the actual computer inside. I, of course, don't know how computers work. I mean, now I do, but at the time I didn't. Now I do a bit. The logic gates I was familiar with. I hadn't ever built them in Minecraft, but I was familiar with the concept. But how do you build a computer? Like, fundamentally, I have now these gates. What is the next step? I have no idea. I did not look at other Minecraft computers at all, ever, during this process. I've seen showcase videos, but I've never watched an explanation of how these things work. So I did, on the Minecraft perspective, come up with all of this stuff, except for a few exceptions that I will note from scratch. On the computer architecture side, I came up with basically nothing because I'm not going to invent how computers work. What I did instead is I used a book that is part of a course, which is called, I need to quickly tab out, it is called The Elements of Computing Systems, Building a Modern Computer from First Principles. And it is part of, or it is the compendium guide to the, let's say, project that is called From NAND to Tetris. So the concept is you start implementing logic gates, as I did in Minecraft here, but there you use some hardware simulator. And from that on, you step by step build up the components you need, and then you build up an actual simulated computer. And it starts with NAND gates, which in theory can be enough to build the entire computer, and you end up with a machine that can run Tetris. And it starts off with a big hardware block, and then comes a big software block. I only dipped my toes into software because this computer is not good enough to handle more complex software. It can conceptually handle it, it is just far too slow and has far too little memory to actually do so. So I used this book as a guide on how computers work and how they are constructed, with the added difference that I did not use their tools or anything. I built things in Minecraft, and whenever it suited me to slightly deviate from what they were doing, I did so, but I followed their architecture structure. Because again, I'm not going to come up with how computers work, I want to learn how computers work and build one in Minecraft. And the next step after these logic gates is a half adder. This is what I came up with. A half adder takes two input signals and has two output signals. And those output signals are a sum signal and a carry signal. And what this means is, if I turn on this left lever, the sum turns on. So my sum is 1. And if I turn on the right lever, my sum is 1. But if I turn on both levers, my sum turns off again, and instead the carry signal turns on. So you can already conceptually think of the sum as an exclusive OR, in that if one or the other is on, the sum is on, but if both are on, it is off. And the carry is then the outcome of an AND gate. So this is my actual design. I did not use this XOR gate. Again, it was 3 weeks ago, so let me remember. I used an OR gate and an AND gate into X and not Y for the XOR. And then I have the sum signal, and the AND that I already had before I used as the output of the carry. And now I'm adding some verticality into things, because the issue with Minecraft is how redstone works. If I place down a redstone and another, they connect and form a line. But if I form two lines like this, they intersect and they form one thing. If I want these two not cross each other in an annoying way, I need to do something like this to have one signal run over the other. And this, you can maybe already start to see, takes space. So this is a somewhat compact but not necessarily super readable half adder, where I will explain it because it is fundamental. This up here, this signal I split into two, and one of those signals goes into this comparator. Now, it's already obvious that the other signal also goes into this comparator. So this comparator is my OR gate that I use for this XOR outcome of the sum. I then also need to turn this off if both signals are on, and this is this repeater here from the side, so this is the outcome of the AND gate. Now for the AND gate, what I need is to route two signals onto this side. So maybe starting with the Y signal, I run it into this comparator here, but the signal is turned off because this redstone lamp up here powers this redstone wire, and that turns off the comparator in subtraction mode. So I need to also turn on this to turn off this lamp, that this comparator can send signal into this block. This is an important feature of redstone that a signal sent into a block powers that block. Now the entirety of this block is powered. But if I put just some redstone wires, it will not act like it's powered. Like, you will not see that it is powered. If I put a lamp here, it will turn on, however. So this is a concept I was fortunately already familiar with, which is soft and weak powering, where this is now soft powered, which means certain blocks like a repeater can be powered from it, but a redstone wire will not be powered from it. This here works only because the wire runs up the side, but the second I do something like this, that this can't move up here, it's turned off. But a comparator signal into a block will mean the block is now strong powered, which means that the block can also power redstone wire on the side or on top. So that's quite an important distinction that later on will be very relevant to how I build this computer. For now, this signal now weak powers this block, which then will still turn on this redstone repeater, and I get my sum and carry signal. So this is the basic component of a computer, or rather of an ALU, an arithmetic logic unit. It is very important, but it is also just a tiny fraction of what makes the computer work. It is also only a half adder, as this already says. A full adder is the next step. A full adder requires 3 input signals and the same 2 output signals. And I was confused by that at first, like, why do you need 3 input signals? And the reason is that this carry signal represents going to a higher order of magnitude. Now, in a decimal system, it is what we do when we, let's say, add 7 plus 4. We will say, okay, 7 plus 4 is on the lowest order decimal 1, but then we need to carry over the additional 1. For 7 plus 4, it's not that relevant, but if we add 211 plus 942, I selected numbers which don't actually carry. That is genius. But if we do some more complex addition, we might need to really think about that carry, and that is what you learn in school. The only difference is a computer, of course, uses binary. So we work in powers of 2. So if we say this is the lowest order and we have an input of 1, then the output is 1. But if we have an input of 2, the output of this lowest order is 0. The output of the order 1 higher is 1. So we have 0 times 1 plus 1 times 2. But that needs to be added onto the input of the higher order. So now we have the same idea of an adder and half adder here, but we just connect another half adder to it, and we connect a third input signal to it. And this third input signal, you can see, is connected to this half adder as the same as this input signal of X would be to the first half adder. And ultimately, what this does, this is neither optimized for space nor for speed. True, but I ran with it anyway. The actual computer uses this. Is, for example, I say I have an input of 1, or I have 2 inputs of 1. Now the carry signal turns on, but I can also have the third input signal, which will turn on both. And all of these inputs, and that is what makes it complex, are equivalent. At this point, there is none of this if X then Y shenanigan stuff. All of these inputs, all 3 of them, are equivalent. It does not matter. It only counts how many I turn on. So now 1 is on, so we have a signal there. Another 1 is on, we have a signal there. Another 1 is on, we have a signal there. At a second one, this turns off, this turns on. Doesn't matter in which combination, all 3 are on, or 3 are on. And this is now a full adder. And the reason we need these 3 inputs is, as I said, that we need to be able to carry the inputs. And this is what I did here. This is the step where I really, when I read it in the book, had an aha moment of, okay, I'm starting to understand. So I am now connecting 4 of these things. These are just copied and pasted with world added. Without world added, this project would not have really been something I would have wanted to do, because I would have needed to place every single block by hand when certain patterns repeat. That is not worth it. I use world edit. I select the corners of the thing I want to copy. And now I made a mistake, but I select the corners of the thing I want to copy, and then I copy it and go to the location that I wanted, and then I, let's say, rotate it by 90 degrees and paste it. And now I made a mistake in selecting things. So I have this half-flying redstone torch, which of course is not sustainable. The second this gets a block update, it will... I don't know how to... like this. Maybe World Edit is more robust with block updates and destroying things. Doesn't matter. This makes it a lot easier to build stuff like that, where you just need to copy things. So now I have 2 inputs into this. Also this third one, which is not really needed because it is the carry and there is no lower order. And this is now the sum of order 0. And this carry signal moves over into the input. I slightly modified how this works. Here I use a half slab, which does the same as a glass block, which I demonstrated earlier, that the signal can only go up but not down. The sum of the second order, third order, fourth order, all of these are wired up. And now I can say, let me plug in some number here on the top, like 5, and then let's add to 5, maybe 7, 5, 7, as the kids say. And then the outcome, what is 5 plus 7? Let's have a look. It is the, this is the 1, this is the 2, this is the 4, this is the 8. Turns out 5 plus 7 equals 12. So this will add 2 numbers together. And all it really does is, as in this case here, both of these are 1 on this bit, on this order. So the sum is 0 and the carry is 1. And that carry now moves into this full adder. This full adder takes another input, which is 1, and then an input, which is 0. So now there are 2 inputs of this. So this is 0 and the carry is 1. So you carry 1 signal over here. On the third order, you take 2 inputs. So now you still get a carry signal, but also this turns on. And on the last order, you don't get any inputs. So your input is only 1 of the 3. So you don't get a carry and the sum is on. And now we can, until we run into numbers which are too large, reliably add numbers. And here we already see that every single one of these things we add will expand the largest number we can possibly add together, because it is the largest number we can put in and the largest number we can display in the output. And this is now 4 inputs. So this is a 4-bit adding machine. And the largest number of 4 bits is 8 plus 4 plus 2 plus 1, which, well, is 15. 15 is not a particularly high number, which is why 4-bit computers are not really a thing. And this is where I started to actually build what ended up being the proper computer, which is a 16-bit computer according to the specifications of the book. The book, by the way, I found on some website. I'm sure it's perfectly legal and all is fine. So this is the first order. You see here the carry input is not used because what would it even mean? So in theory here on this order I could simplify things a bit by only having one half adder instead of a full adder, but for simplicity and understanding I don't. Now you see the machine is doing things. I need to quickly turn that off because otherwise things get confusing. All right, I've taken the liberty of turning not just the machine off, but disconnecting part of the machine, that for later demonstrations I will have an easier time showcasing what I'm actually doing here. So I showcased 4 of these adders in a row. Now it's a 16-bit computer, which means we have 16 of these. And this is why computers are classified in things as like, this is a 32-bit computer, this is a 64-bit computer, because here at the fundamental level of, for example, this arithmetic logic unit, which is a bit more than just these adders chained together, it will take now an input signal, or rather 2 input signals that are 16 bits long, being represented by 16 separate lines that are either on or off. And because this is Minecraft and 2 adjacent signals are not independent anymore, having a 16-bit signal requires 32 blocks, i.e. 32 meters of space. And this is why this entire contraption here is so massive. Obviously, it is possible to slim this down, and I learned over the course of this machine that it is very desirable to stack things vertically. But in the beginning, I laid it all out on the ground, or much of it. So I copied and pasted. This is what these black boxes are for, that I know where to stand when I'm pasting things. 16 of these in a row all the way up to here. And then I wired up inputs for all of these. And you see these repeaters because signals only travel 16 blocks. And this is the first opportunity for me to talk about signal travel time, because each of these repeaters introduces a 2-tick delay. Now, Minecraft has a tick per second rate of 20, as I'm showing here. And 20 ticks per second means that the game 20 times per real life second updates what is happening. And it is good to showcase this, so I am using the incredible carpet mod, and I wanted to type carpet because I said carpet, the incredible carpet mod to freeze it. So now you see the TPS, the ticks per second, is at 0. And if I do something like this, I can still interact with the world because this does not have a delay. But if I add a repeater to this, the signal does not pass through. And now I can do a tick step. The signal does not pass through. Another step, and now we have a signal because the repeater introduces a 2-tick delay. So in other words, if I want to send a signal from here all the way to the end of this thing, I can maybe do tick step 10. And you see within 10 steps, the signal traveled until here. Let's do another 10 steps. The signal traveled until here. So this was 20 ticks, which means 1 second. So it took the signal 1 second to travel from back there to here. That's not super slow, but consider that this here, this adder, also has a lot of things like repeaters, which introduce a delay in the system. So I'll add another 10 steps. Now the signal has reached here. Let's go a bit slower. Let's do 2. Now the signal is going here. Another 2. Signal has moved here. Another 2. And now we get an output. This signal only needed to pass through because it is only one signal. The second these circuits start to take some time to reach their final state, because this is also doing calculations, and only when this is done will it send the carry signal into here, it will add quite some delays, and now this signal needs to travel back. So another second, and the signal is now here nearing the output of this adder. So just sending a signal without it actually having to do many calculations from here to the very end takes quite some time. And now you already see also, if I do another 10 steps, that the delay is also true for turning off a signal. This you can think of as the speed of light. There are ways to transfer signals faster, but I am not using any of them, and I don't think they are really usable in the context of what I'm doing. So think of this signal travel time, that every 16 blocks you need a repeater, which means 2 ticks, i.e. 1/10 of a second delay. That is the speed of light. We don't get faster than that. And combine that with the fact that the game requires you to build quite big, and you start to realize why the machine that I built is very slow. But this adder works. There are ways to speed this up, by the way. There are ways to build a thing which already predicts how many carry signals will reach the end and will speed it up and not require it to do each of these calculations in sequence. I did not implement one of those. It would probably be smart, but I wanted a working machine. I didn't want an optimized machine. Otherwise, this would not look as it does. But I think with this, it's at least quite understandable of what this does do. So now I can, in theory, if I want to, like show, yes, this does really work. Let me grab a redstone block, and let's say I want to add 17 plus 12, which, to be fair, is not a super large number, but I don't want super complicated calculations, so I'm putting this to 1, then no 2, no 4, no 8, but a 16. So that's 17, and then 12 will be a 4 plus an 8. So these signals travel and turn off and on things, and now we figure out 17 plus 12 is actually, it's 1 plus 4 plus 8 plus 16. So this is 24, 28, 29, which is indeed 17 plus 12. Right. So it doesn't help that the lamps at the end don't light up, but again, there's a reason for that. So this adder, all it can do is add numbers, and that's quite limiting, right? We want our computer to be able to do more than to add numbers. It's supposed to be a general problem-solving machine. So, for example, how do we subtract numbers? And there's actually a pretty simple answer to that, and that is to say, this here, this last bit, is not used for positive numbers, and this is how we come to signed and unsigned integers. This machine assumes signed integers, which means this is a 1, this is a 2, this is a 4, 8, 16, 32, 64, 128, 265, 56, 512, 1024, 2048, 4096. I don't know what that number is. I don't know what that number is, like 16,000. And this is used to represent negative numbers, but it's actually quite clever in that negative numbers go the other way around. If all of these signals are on, like the entire input on all 16 bits it's on, it's -1. So after the highest positive number, in a way, if all of these are on, it is -1. If you want it to be minus a large number, only the last one will be on. And that makes the calculations just easier. Now we have a problem, and that is, okay, so in theory this machine can subtract by adding a negative number. That's cool. But if I want to do certain operations, like adding +1 or subtracting 1, very common operations that computer programs do all the time, it would be a lot of work, because you would need to write that number into memory and then do some operation with that number. But how do you even write a 1 into memory? And you start to think, okay, maybe these super basic operations are good if they are included. And this is what the ALU, the Arithmetic Logic Unit, actually does. Because not only does it take two 16-bit inputs, which are these two lines here, it also takes certain control inputs. And these controls I'm representing in this blue, with these blue wool blocks, do certain things. And what they're supposed to do, again, it's all from the book. How I do it, I came up with myself. One is I want to be able to zero the inputs, meaning no matter what the input is, no matter if this is on or off. Right now these are on and it just carries through, right? These are on. But no matter if they are on or off, I want to be able to turn them off. And the way I do this is to just have a bunch of pistons extend and block this path. So now the signal cannot travel into the next block. The same here on the bottom for X. Only difference is this half block is needed. If I put a wool block here, glass block would be fine, but if I put a wool block here, it would break the machine. It is very deeply stupid, but I suppose I can explain that because it's, yeah, it was a bug I had. If I turn on this piston and now I turn it off again, well, I'm not turning it off. Why am I not turning this piston off? Because this redstone line is weak powering this block. This block is not connected to this piston, yet this piston still feels its power. Why? Because of quasi-connectivity. It is a bug in the game that is intentionally not fixed because it is actually used for quite some things. And quasi-connectivity is, for example, used if I do something like this. This single signal will power both pistons. And again, it is weird in how that works. This, you see, does not work. And the reason it does not work is that this piston does not receive a block update because it's Minecraft. This is actually the type of stuff I am familiar with. This is where my game knowledge did help me a lot. But this powers the piston, but since it is not adjacent to the piston is not updated. Only when you do something adjacent to the piston is it updated. This is very stupid. It is, technically speaking, a bug, but it is intentionally not fixed. So in order to avoid that, I'm using here a half slab, and that half slab, now if I update the piston, the half slab does not transfer signals because it is transparent. This half slab cannot be powered. It works. All right, next thing, I want to be able to invert the signal, meaning right now these inputs are 1 and the rest are 0. These inputs are 1, the rest are 0. But what if I want to flip that? And that is this input here. This is the invert input. So now that I'm powering the invert control, all of these are 0 and all of these are 1. And why is that relevant? Because, as I already said, this is how negative numbers work. This here is the number -1 now. So now that I'm not inputting anything, but I'm inverting it, so I could also say now that I'm not inputting anything, right? No matter what is in here, I'm not inputting anything. this outcome of this number is now -1. It's still not back there for another reason, but I'm now coming to that reason. So I'm doing two things to the input. I am setting it to 0 if I want, which I do with these pistons, or I'm inverting it. And this inversion thing is a bit weird because what I'm doing here is I'm effectively moving a block back and forth, right? That is what this signal does. It powers this line, which powers this redstone torch, which powers this piston here. And if the piston is in the default position, this signal here is powering the piston, strong powering the piston, which allows this wire to be weak powered and transmit the signal. So if this input is 0, then let me quickly do it. If the input is 0, then this is off and the output is 0. But if the input is 0, this goes into this redstone torch, which means this redstone torch is active by default and it's sending an output signal. So these signals are always inverted because one uses a NOT gate, i.e. a redstone torch, and the other does not. So these are always inverted. And what this control here does is it controls which of the two signals I'm actually taking. Because if I'm putting it on, here you can't transmit a signal through the piston itself, the piston head itself. It can only go through the block. So I'm flipping which signal's actually taken, and the same down here for the other input. So now I have 4 controls: zeroing X and Y and negating X and Y. 4 ways to control the input. I also have 2 to control the output. And one of these is very similar to what I just showed, in that it is flipping which signal is being taken. It is done in a bit different way, but again, I have 2 signals here, this one and this one, and if the blocks are raised with these pistons and honey blocks, then it can only go through the top level, and this left signal here is taken. If the blocks are lowered, it can only go through the bottom level, and this lower right signal is taken. By the way, this does not work with slime blocks to move these blocks. It does require honey blocks. Honey and slime blocks are very similar in that they stick to things and allow pistons to move multiple blocks, but they are not identical in that a honey block is just slightly transparent here at the side, which means you are just slightly lower. If I'm activating my HUD, you see I'm at Y minus 62, and I move to the honey block and I'm at Y minus 62.1. So this is 0.1 meters in all dimensions smaller, meaning it is not a full block, and it not being a full block means it cannot transmit a signal. It is not possible for a honey block to transmit a signal. A slime block can do it. Praise be to the honey blocks. Without them, this setup would not work. So this is what it does on a mechanical level. It again takes one or the other input, but what is the other input? And I'm writing here add or bitwise AND, because there's another thing I'm doing. These output signals, I am transmitting them to the adder, right there to the adder, and it adds things. And they're always being put to the adder, and the adder always adds things. The question is the adder signal actually taken, or is another signal taken, which is this one that I snuck into the side here, which is the output of this redstone torch, which is a bitwise AND, meaning I need both of these to be turned on. And if both are turned on, this is just a vertical, because it fits better, AND gate. It does the same thing, that I'm negating both signals, and then I'm combining them, and then I'm negating the output. So only when both are on does this turn off, and only when this turns off does this turn on. So this is a very space-saving way I found to combine the input switches, these 4 input switches, and then also the negation. What is not space-saving is having to route the signals like this, but again, I didn't iterate on this at all. This is just the first thing I built. So now I have a combined signal of 1, as in only the first bit has both ones active. But now if I power this, I am flipping which signal is actually taken, and the output here is a 2, because I'm adding 1 plus 1 equals 2 via this adder back there. So I don't have any logic in here that route signals differently. Both the bitwise AND operation and the adder operation are always running. What changes is which of these signals I'm actually using, which can go further. And that is controlled by this. And then there's one last, which is the same building block I used back there, which allows me to invert the Y output. So it does the same thing. Now, instead of having the 1, I now have everything active except for the 1. So this number would now be a -2. And again, this inversion useful because of adding and subtracting and these things. I, of course, again, did not come up with these things. There is a table in the book which explains how operations work. And that is what I'm going to show next. All right, so this is a screenshot from the book. And either this very legit version is not very legit, or for some reason all the figures are low quality and the typesetting is very weird. But it is showcasing the ALU as a chip of what it's supposed to do. It's supposed to take an input of X and Y, 16 bits each, which we have here. It is supposed to take 6 control inputs, which is zeroing X, negating X, zeroing Y, negating Y, all of which is performed on these 4 inputs. And then it's supposed to take F. F is this one here that allows me to flip whether to take the logical AND or the addition. And then there's the negation of the output, NO. And the output is a function of X and Y, and I suppose all the control variables, which is 16 bits long, which is this chain of redstone lamps here. Also, there's an output that will tell me if it is 0, the output, or if the output is negative. That is somewhere up there. It does not matter for this stage. And I only added that way later. So this tower has a few more than just the lines going over there, but it does have all of them. So given certain X and Y inputs, which also come from here, I can now perform certain operations. Which operations can I perform? Well, that is given in this other table here. I can perform a combination of operations based on the combination of these input control variables. For example, I am now just setting some random, this doesn't really work as I wanted to, just some random numbers for the input of X and Y, just anything really. So this is whatever, my input of X and Y, and the output we get from that right now is all zeros because I don't have any same one. Maybe let me also add that so that we get at least one output, and here you get a slight feeling for the delay of that was the logical AND. I can now maybe flip and show what happens if I'm using the addition. This would right now be the outcome of the addition. Let me remove this one real quick. And eventually it will change the outcome, but you already see there's quite the delay in there. What is nice about this entire setup here is that it is a circuit that has certain inputs and certain outputs, and nothing happens in between. Oh, there are the logic gates, but no states changes. The outcome will always be the same, and it is exclusively determined by the inputs. And it might take a bit, but after a certain time, this will stabilize. All of the operations that go on, if I'm doing something here, will stabilize, and the outcome will be what it is. For example, if I activate this, which should be zeroing x, I suppose. I can't quite see. Let me check what that is. It is zeroing x indeed. I am getting some other output. If I'm removing it again, some things are happening here in the adder, and it will reach the final state. So this does not have to be reset in any way. I don't need to toggle something here. I just need to wait for long enough, and then my operation is performed. And that is already quite nice, I think. So I am now able to perform operations. If this F signal is on, I am just adding, right? If none of the other controls are on, I'm just adding. But this table, oh yeah, I still had the thing shown, so maybe you couldn't see my block placing as well. But this table, for example, tells me what I need to do if I want the outcome to be 0. And you could think, well, if I want the outcome to be 0, just set all of these to 0. True, that would work, except that's not really useful because these inputs will always go into this ALU, and they will depend on some values that are written in some registers. And you don't want to just overwrite the registers just because you want a 0 for some reason. So what you can do is, and this is, I suppose, rather obvious if you think about the options we have. There are some other things here, but we can 0 x, we can 0 y, and we can do f, I think is still already on. Based on this thing here, I can maybe use the lever instead. And our output is 0, because no matter what the input is, I'm using the zeroing functionality to just set them to 0, right? I don't want to set them to 0 on this level here. I want to set them to 0 inside the arithmetic logic unit. Now, I already said that it is maybe desirable to have certain common values like +1, -1. And this already tells us, okay, if I want it to be +1, then I need to 0 x, but also negate x, which right now we're not doing. But also I want to negate y. So let me negate y real quick. I still want to have this F toggle on, so I still want to add. I'm talking about +1, I think, right? So then I also want to negate the output. So now all of these 6 controls are turned on, and my output is 1. And we can think about why the output is 1 and come to the conclusion, okay, we first 0 everything, then we put everything to minus, so we negate everything. So now all of these signals, both of these signals, are fully on. And we could say, okay, let's add -1 plus -1. What will the outcome be? Well, the outcome will be -2, obviously. But it's not so easy. We're negating the output again at the end. And if I'm not negating the output, we can have a quick look at that. So I don't want NO. indeed, this is the representation of -2, because we're calculating -1 plus -1, and this is -2. And this is why this formulation works so nicely, because we can just add negative numbers and in that sense subtract. So now the outcome is -2, but you see -2 is represented by all lights being on except for the first one, and then, well, then let's just invert the first one, and we get what we wanted to get, which is only the first one is on, which is a 1. And there are other functions in here, like just taking the x, not taking the y, just taking the y, not taking the x, taking the opposite of x, taking the opposite of y, always the bitwise opposite, taking -x, taking -y, x plus 1, y plus 1, because as I said, these are very useful common operations. We now have the operation 1 in there. What is the difference if we want the operation x plus 1 instead of 1? Well, maybe also quite intuitive. We of course need to turn off the thing that zeros x, and now whatever our x signal actually is, we're adding 1 to it. Can maybe see it is these 3 things that are on. These are these 3 lamps, and now also in addition to it, the 1 is on. And there are some more like and or operations that we can perform with this. So you can already see at this level, just with these 6 control levers and these inputs, we have quite the ability to not just calculate basic arithmetics, but also to do some logic, because all of that logic of certain calculations like this, of comparisons of 2 values, needs to be performed in such a manner. Now, you might see that there is no multiplication, no division in this. And that's true. This machine cannot multiply internally. And I will come to multiplication, and I will showcase multiplication, but that is way down the line. Multiplication, difficult issue. All right then, next step. We now have an ALU. It works. It does the operations that the ALU is supposed to do. So what was the next thing I did? I moved to a different place on the map, and I wanted to build memory because, and that is very important, this circuit, as I said, is only dependent on its input states. It does not store anything. And we need to store things. And storing things is actually the next step in the book, and it is also the next step in what I did. Oh yeah, I came up with some other things like this input selector that I showcased earlier. I did also build here, so I suppose I could have shown it here isolated. This is the vertical NAND gate that I use for the AND operations in there. And this is the mechanical, I call it the mechanical XOR gate because it is technically speaking an XOR gate, but it is mechanical in that it uses this piston. And of course, as far as the logic is concerned, it does not matter at all, but this is what I also use in this block back there. But that is not what I want to show. What I want to show is memory. And I suppose in this version of the world, I already removed the basic showcase. So maybe I will quickly rebuild that on the fly to show what I decided to use for memory. It is, oh yeah, I have it here. This is one of the few times I did use an external source. Not for how do I build memory in Minecraft, but for I want to do this very specific thing. How do I do this? And what I'm using is a relatively new redstone component, which is the copper bulb. The copper bulb is very different from the redstone lamp that I only use for showcasing things, but that does not actually serve any purpose on a logical level in the computer. The redstone lamp is on if it gets a signal and off if it doesn't get a signal. The copper bulb is different in that it is on if it gets a signal once, but it doesn't need a sustained signal. And if it gets another signal, it is turned off again. So it is toggled. If you send it a signal, it will switch state. And this is why I decided to use this for memory, because I thought no matter what the input is, after I first set it, it can turn off again. It won't affect the state of the copper bulb. So this will, independent of any circuits, store its current state. It will only change its state if it receives another new signal. So if it gets one signal and that signal keeps being active, nothing happens. It needs a new signal. And the reason this is useful is that you can attach a comparator, one of the greatest redstone blocks in Minecraft, to it, and the comparator will read the state of the copper bulb. So the comparator will turn on if the bulb is on and off if the bulb is off. The comparator is very versatile in that regard. That also works for other things like this redstone lamp. Oh, this is actually not a good comparison because this is a repeater. And the reason this works also with a repeater is that I'm soft powering this lamp. So I suppose this is not a good way to showcase that it also in theory works with a lamp. But you can read all sorts of states with a comparator. You can read the contents of a composter, for example. So if I'm now taking some leaves into the composter, it will turn on and the signal strength will increase the higher the level of compost in the composter is. So the comparator also reads block states. And again, I'm not working with signal strength, but reading a block state is very useful if I want to work with memory. It is possible to build mechanical memory using like a chain of redstone repeaters like this that always power each other even when the input signal is gone, and then maybe use a piston to disrupt the flow of the signal at a certain point to prevent it from continuing. I've done that once in the only real logical redstone thing I ever built. I did build one thing like a decade ago where a single bit of storing a value like this does now was like a 10 by 10 massive construction, and the only thing this thing could do is count. But that was before copper bulbs, I suppose. So I chose to go with copper bulbs. And then I noticed two issues. One is I want to store 16 bits of data. If I put copper bulbs like this, I can input 16 bits like this. Seems fine, right? But I also discovered, okay, sure, but I need to be able to reset the copper bulbs. And there are some other things I want to do, like preventing it from getting multiple signals. So after my experiences, because I am telling this chronologically, after my experience of how much space this stuff here takes, I decided let's stack it vertically instead. And the other advantage of stacking it vertically is that you can much easier access it from the side, even from two sides. You could access the other thing from the bottom, but that is not nearly as convenient. So I built this, of just stacking them vertically. But there was another issue with the copper bulb design, and that is, okay, cool. I get a signal, I can store that signal on 16 bits into memory, and then the copper bulbs will have the state of that signal. Perfect. Right? This is 1 and a 4, so this is a 5. That's cool. But how do I now overwrite this? If I want to take this and instead of writing a 5 into it, I want to write a 1. I could now send in a signal that is 1, and all that would do is it would turn off this lamp and my signal would be 4. It's not very useful, is it? And that is why I needed a way to reset the copper bulb before storing a new value. And that is this design from Trick Engineering 45 on Reddit. That is what I looked up. How do you reset a copper bulb? And the answer was use another mechanic that I did actually forget about. And that is repeater locking. And repeater locking is complicated in that it's a very weird and very old mechanic. And essentially what repeater locking does is if I'm placing a repeater on the side of another repeater and that repeater gets a signal, this repeater now here has this bar which prevents it from transmitting a signal, right? No matter what the input is. And now that I turn it off, it transmits the signal again. But there's a reason I didn't use this for the earlier gates. And it's not just that I forgot about it, but also that the repeater locks the state of the other repeater. It does not perform a logic operation. Now this repeater stays active because this is active. But if this had first been inactive, the output is different. It is not just an output of the inputs, it is a matter of order of inputs. And repeater locking I only ever use for this setup that I got from Reddit, because what this does is actually quite clever, which is why I used it. By default, this copper bulb is in some state, and this repeater here is locked, meaning no matter what the state of the copper bulb is, no matter if there is an output or not, this signal will not go into this target block. But if I am sending a signal to this copper bulb and the output is 0, it will unlock this repeater for the pulse length of my signal. So now this repeater can transmit a signal, but there is no signal, so nothing changes. But if the copper bulb is active and I unlock the repeater, this signal will go into here, will go into here, will go into the copper bulb, which will then turn it off. And by virtue of turning it off, that repeater is turned off again. So by the time this pulse is reactivated and the repeater relocks, it is off and it doesn't lock it in the on position. And this I can stack as a vertical tower quite easily by using a redstone ladder. And what a redstone ladder does is it travels upwards quite efficiently because it uses half slabs, which have the same effects as glass blocks in that it can only move up, but it cannot move down. I do need a signal extender here to get to the full height of the tower. I actually need 2 to get to the very top, but this is still pretty lightweight. And now I press this button and it turns off all these redstone lamps, which means it turns off all these repeaters, which means it unlocks all these repeaters, which means it resets all these copper bulbs to 0. No matter what the signal prior to this is, like I can put in this signal, this is now stored, I'm pressing this button, it's reset. And this is really, really useful, and this is how I handle memory. So yes, this Reddit post helped me because I couldn't quite figure out how to reset copper bulbs for the simple reason that I forgot about repeater locking, and this is quite an ingenious way to do it. It would be possible to do it without repeater locking as well, but I'm quite happy with this solution because it also doesn't take up too much space. The issue is I need more. I also need to be able to control when I send a signal, because the moment I unlock these repeaters to reset the state is when the system is vulnerable. If I would send a signal into the copper bulb now, it would allow the system to activate the copper bulb again, and then this repeater will be locked in the on position and everything will break. You will need to manually fix it. You cannot press a reset button somewhere. You will need to just destroy and replace the repeater effectively. And this happened a few times when some things were still wrong in testing. Actually, I figured out that I need a longer input delay on this for this to work in all cases. And the way I handled this is I'm just saying, let's first reset and then move in these blocks. By moving in these blocks, this signal here can be transmitted. So first I'm resetting the state, and then for a few seconds I allow it to, a few seconds, for the pulse length of this signal here, which can be like a fraction of a second, I allow it to read the input states, and then it's disconnected from the input, and no matter what happens here, these copper bulbs will stay in their position. The other thing I need is I need to control output, because for a single memory it is enough to just read the output like so. But I want RAM, I want random access memory, and I also want my instruction memory, my read-only memory, which technically speaking you can also write to, but not the computer can't, I can. And that way I need to route things. And that was the next step, figuring out how to properly route things. And this is how we come to these blocks here. This is a bit more iterative. I added onto this later, this bottom layer and this green signal and some of the other stuff that's going on here. So what am I doing? I am following again the book, which tells me you build different levels of RAM. For example, a RAM that consists of 8 16-bit storage spaces. So each of these towers here can store 16 bits, and I have 8 of them. And I need to be able to address them, and I need to be able to write to them, and I need to be able to read from them. So I have an address input signal, which is these 4, 2, 1. I need 3 bits of input to address the 8 towers. So if all are off, this tower is addressed, which means right now, if I would write, this is some arbitrary input signal, for example, a single 1. Let's make it a bit more interesting and let's make a 3 out of it. If I now load, I am performing a chain of operations which first resets the state of only the memory that I want to read to, load data into, and then it allows it to write for a fraction of a second, which these pistons here do, and then it doesn't allow it to write anymore. And the way I do this is by addressing the correct memory, which is at this point just the same logic gates I used before. And it really is that simple. I just looked at those gates, which in this world are still over there, right? I just flew over there and looked at, wait, which do I need? And then I built things up. So for example, if I want to write to, number 4, so let's starting count from 0, I want to write to number 4, which is the 5th of these, right? 0, 1, 2, 3, 4. I'm flicking this 4 lever. And what this 4 lever does is it, first of all, blocks the input for all lower things, so that I don't have an input into anything below 4. 4 is handled a bit differently from 1 and 2. I wanted to keep it somewhat space efficient. I don't want a 3 input gate for all of them, so I just made 2 input gates and then had the 4 toggle things on and off at a more fundamental level with these pistons to just prevent the signal from traveling up here. That's what this is doing. I'm preventing the signal from traveling up here into this redstone torch. And this redstone torch is what toggles this pulse here, which controls my reading. So it controls which of these outputs are active. Now this reading is active, so the signal can travel through these blocks, and all of these read signals are connected. All of them are the same and have the same output at the end. So I only ever want to read from one of these, the one I actually want to read from. And that is what these redstone torches here do. What also happens is I'm sending this load signal, which has here a bit of fancy trickery to use a rising edge detector. This is another thing I looked up how to do, a rising edge detector, which the second it gets a signal, it will extend this piston, and that will prevent the signal from traveling further. So it's only sending a short pulse. And that short pulse first resets the copper bulbs and then allows writing to the copper bulbs. So that is what the load signal does. The second I trigger the load signal, it will reset the state and then allow the system to load things into memory in exactly the same way as I did back here with this button, with the main difference being that now this load signal also only travels to the one point I actually want to load into, and that is controlled by this, what is it, X and not Y thing, where the load signal, if I activate it, will deactivate these, which will allow signals to pass through the comparator, but only in the one that I'm actually writing to is the signal actually active. So this was, I think, the hardest part of the redstone of the entire computer. Figuring out how to wire up things that at every time just I can put in a number here and I'm addressing the correct register. But all I'm doing at the end of the day, besides this piston trick, is I'm reusing the same gates I've used before. And so I'm using these things where I'm putting in these inputs of X and not Y or whatever in the correct order, flipping which one it is, using AND gates in certain places to make sure that only ever the one that I actually want to address is active. And this is unlike the adders in that it does matter which signal this is. These are not just the count of signals. So this took me like 2 evenings, I suppose, but I did figure it out just by knowing what I want to achieve, which is not that hard. I just want to address the correct of these 8, and then using the building blocks I had before to do it. So this is now an 8 RAM, so it has 8 16-bit blocks. And then I took this and I copied and pasted it 8 more times. And this is the 64 RAM that I'm actually using. I could copy and paste this 8 more times in this direction. It is designed to allow for that. So now it takes an input here, and that input now goes into all, you can see, it goes, this signal is on, it goes into all 64 of these. I'm not deciding where the signal goes. All I'm deciding is for which I trigger the load signal, right? That is the only thing I'm actually deciding. And that makes the logic a lot easier because I can just copy and paste the 8 block, and now all I need to add to that is the logic of which of these 8 blocks to trigger, right? Which one of these 8 blocks to address. Because I already have the logic of internally with the 1, 2, 4 signal, which ones inside each of these to address. Now I just need to add to that the logic of which of these to address. So all of these gates I'm using here are exactly the same contraptions that I'm placing down there, just rebuilt. But these are the same ones that are down there inside the 8 circuits. The only thing is that in addition to it, I'm also now transmitting this signal of the internal 1 to 4 ones into each of these. And of course, I'm transmitting the load pulse into each of these. And this is working RAM. This is working memory that I can tell the system to address. And here you see these I needed to increment by 1, because otherwise the load pulse, the reset pulse could be too short, and that could randomly lead to disaster. I didn't have to do a lot of debugging, to be honest, because I built these components individually, as you see here. And the second this component works, it mainly also worked by integrating into the entire system. This computer is not simple. I won't pretend that it's simple. But what I will say is, even though I'm now talking for like, I don't know, in total 1.5 hours at least about how it works, it's modular. I built it piece by piece and then just combined the pieces. And combining the pieces was often the hardest part, because the internal logic of what each piece does was fine. Combining them all together, that wasn't super easy. Figuring out what needs to go where wasn't super easy. But I knew at a certain point, like, okay, now I want to connect the RAM to my computer. So I copied and pasted this thing from back there over here, rotated it, and then connected all the wires. What I'm connecting it to, that is what I'm talking about next. All right, let's get back to the ALU. The ALU works. It is self-contained, you could say, with certain inputs and outputs, but of course, in the logic, it is not self-contained. It needs to be connected to an overall machine. Otherwise, what is it doing here? I'm not manually flipping levers to tell it what to do. So now we get into, I'm ignoring the purple for now, we get into the registers. I showed how the RAM works. And these registers are just a single tower each, with the same logic of being able to reset the copper bulb and then sending the load signal and having a toggle of whether or not to read. With the difference being that this tower always reads. So there's no actual logic there. This is not needed. This is just, in theory, I could do something with that, but it's not needed. This one is actually needed of whether or not to read here. Except there's also a bypass. So let me talk about registers. There are 3 registers as far as the instruction to the computers are concerned. Physically speaking, there are 2 registers, the A and the D register, which I labeled with these floating letters to know what I'm doing. And all of this here, by the way, I'm ignoring for now. I'm just following the white lines. So I'm sending the signal from down here up. I'm stacking it vertically. Finally, that is a lot nicer. What I need to do to send it up is also to extend the pulse, because it only goes 16 blocks. So whenever it reaches that limit, I need to put it into a repeater and send it further. Building this actually took a while. It wasn't difficult in any way. It was just annoying. All of the wiring was super annoying. When I'm doing long wires like that back there, that is fine. I can copy and paste these, right? These are always the same. But this, not. I had to do all of these by hand. So I'm sending the signal into this node where it switches and goes into both the A register, the D register, and a secret third location. And the A register and D register use the same logic that I'm only writing to them if I want to. When do I want to write to them? I'll get to that later, but I'm only writing to them if I want to. So let me now switch my instructions a bit, that it's a bit more obvious where lines are active, by maybe flipping this negate output one. So now my signal is -2. And you can see here which of these lines are active. And you will see this signal doesn't actually go into the registers. And the reason for that is the current instruction that is coded does not want it to go into the register. Again, that's something for later. I'm flipping this toggle. Now the signals go into these registers, except I'm not writing to them. I can now send a pulse down here to say, hey, please write into the A register, won't you? And now I send that pulse. Hey, look at that. I've saved the signal from the ALU into the A register. And now this A register is output back into the ALU as the Y input. So it's the upper of these two towers, which is the Y input. So I'm currently negating the output, but let me, not negating, I'm currently zeroing it, but let me change that. I'm not zeroing it anymore. In fact, let me also not negate any of these anymore. And now I'm just adding. I'm adding 2 plus 0 where the outcome is still 2. I'm adding -2 plus 0 where the outcome is still -2. But I could now say, hey, why don't I also write this into the D register by sending a pulse to the D register? And now both of these have the same value. And the ALU now gets the input from both of them, and they're adding it together. And now you see 2 lamps turned off, because now it's -2 plus -2, which is -4. So these are 3, right? These lamps together represent 3, except that all lamps being on is already -1, so this is -4. And now I could write into the A register again, right? And now the A register will read -4. And the ALU is now still adding the numbers up together. And now I am at -4, 5 plus 1 is -6, and so on. I could repeat this operation and I would always subtract 2. So now you already see sort of the functionality of the registers in that the registers are used as the input for the ALU. So if I want to perform any operations, I need to first set the correct values in the registers. Once the correct values are in the registers, I can load those into the ALU and perform the operation I want to perform. And this is where certain things like what I showed before, how do I get a 0 signal, become relevant, because if I want to send a 0 signal, like so, right, now it's 0, and now let's say I'm sending this pulse again. Now my ALU is all zeros. So I can perform operations and save them. But of course, 2 registers is not enough to do a lot. Like the only thing you can conceivably really do with 2 registers is like add the Fibonacci sequence. That I suppose would work. We want memory. And memory means we need to do 2 things. We need to branch off into a third thing and send these signals as well into memory. That part is easy. Branching off, sending it into a third thing, that is not an issue at all. So if I stop zeroing, I'm now just back to my -2 signal, and that is in the D register, right? Added +0 in here. And that also goes off into memory. And I can now address the memory and write into a memory slot. Except how do I address the memory? And this is why the A register is called the A register. It is the address register. And the address register is the address register because it can address the memory. And that is this bypass. No matter whether this reading output is active or not, it is always, the signal from A is always going along these red lines into the memory. And since the memory is only 64 of these towers large, I only need 6. All of these go to waste. In the full specification of what this is supposed to do according to the book, all of these would also be included, or except for the top one, I think, and this memory would be much larger. But there's no need. Like this memory is big enough for any operation I can actually perform. So this signal just is the same that I showed before, that addresses now which of these are active. And right now it's 0 because the A register reads 0, so the very first of these redstone torches and only the very first is active. Works perfectly as I want it to. So if I want to now address the first bit in the A register, or the 0th one, I need it like this. But if I want to go to number, the second one, so number 1, I need a 1 in there. How do I get a 1 in there? Well, I can check the table, and it tells me I need to 0x, negate x, 0y, negate y, have f active, and negate the output. So negate the output, 0 and y, zy, and x, zx. So now it's a 1. I need to write that 1 into the A register, which I'm still doing manually now. So now the A register reads 1. And the red lines here read 1. And they address the system. And now the second one of these is active. So if I now want to write to memory, all I need to do is send the load signal into memory, rather than, for example, sending it like I did now manually with A or D. I can do absolutely the same. Right now I just have a certain value that is still 1, because that is what I am still performing the operation. So if I now want to write 1 into the second of these memories, I just need to send a load signal, and it will write a 1 into this tower. So that is what I'm doing. I'm putting the address of what I want to address into the address register, and then I'm sending a load signal if I want to write to memory. If I don't want to write to memory, I'm not sending the load signal, and I'm still reading from memory. Now I'm still addressing this, and you see this piston is extended, which means I'm reading whatever is in here. So let's quickly modify what's in there that we see the signal. Now I'm reading this, and this output goes all the way back here where all of these join, and then it moves back down a few levels because I was stupid and constructed this stuff on the ground initially. Now I wouldn't do that anymore, but for building it was good. And now if I want to read from memory, I also need to toggle this thing, which tells the system, hey, please read from memory instead of reading from A. So D is the data register, D always reads into X, but on what I'm reading into Y is toggled by the output piston here, which is this blue line, which here reads the activate output of A register to Y input if M is input instead. So I can either read from memory or read from the A register. The A register does a lot. It goes into memory by addressing it, but also the value of the A register can go into memory, which is why I need to tunnel the signal through this output of the D register. And this is where I get into weak power nonsense, where I figured out you can tunnel these stacks of lines through each other without really needing a lot of space by, in this case, I need to go up one level first, but then actually this goes the other way around because this is the output of memory. The input from A to memory, of course, works via the ALU and then on that branch. This tunnels through because I'm strongly powering this block, which can then be read on this side. But here I'm also putting a repeater, and the repeater does not get strongly powered because it's not powered from the top at all. If I put a signal here, it would be powered, it wouldn't work. But with the repeater, both to strongly power the block and the underpass, I can weave these in between each other. And I'm using this quite a few times over here to get signals through these walls of cables. Also here, I'm doing the same. So this was by far the hardest part, figuring out how the, conceptually, not building-wise, but conceptually, figuring out how the A register works was by far the hardest part. But now you see I have this line here, which is the same as this line here, and these toggle whether I'm reading from memory or from A. So I can now, if I want to send, oh, no, this is not what I want. Well, I suppose this one is already active, so it doesn't matter. I can now activate this, and now I'm reading from memory instead of reading from A. So the signal I saved in here, where I modified this redstone lamp, is now going through here and is going into the registers, and I'm now performing a different operation. Now if I, and I'll manually change the register for ease of use, if I now instead address a different register instead of the one I just did in memory, now this piston is no longer extended, instead it's this one over here. So I'm still reading from memory, but the value I'm reading from memory no longer contains this upper one being active that I put in there a bit earlier. So this is really how memory works. It is only the question of, do I want to write to memory, which is when I just sent the green line load pulse. It is the question of which memory to address, which is always, always, always the number that is in A. And it is the question of, do I read from memory or do I read from A, which is handled by this simple toggle of these piston towers. And with that, we are able to perform almost all operations we need to perform. There's one exception, and that is the A operation. All of what I showed before was the so-called C operation, which uses this ALU here. The A operation is different in that if I deactivate this top thing here, I no longer read from the ALU at all. This still does all the things it does. Bitwise AND or adding, it still does everything, but the signal ends up in the void. It doesn't go anywhere. Instead, I'm using this signal from the side, which is everything but the top one, because the top one is what I'm using to actually activate or deactivate this so-called A operation. And what the A operation does is it allows me to write a number into a register. So I set all these things for operations, but let's do something else. Let's write a fun number, like, I don't know, let's choose the very interesting number 5, right? This is 5. And let's write 5 into the A register. That is what I'm doing now. I'm now coding purely in binary the meanings of these signs, like J1, J3, I will go to that, doesn't matter. This is an A operation. This is just the signal 5. This signal 5 goes into here, the signal 5 goes into here, and now if I'm pressing this button, the signal 5 goes into A. And this is how I put a value into a register. And this is how I put a value into a register from instruction memory. And that is very necessary because when I write actual code for this and run actual programs, because this is a computer, I'm doing everything manually now, but this is a computer. It's supposed to run autonomously once I've coded it. I need to be able to say, hey, I need a 17 here. How do I get a 17? This is how I get a 17. I mean, this was a 5, but I could change it to a 17 if I wanted to. And with this, we have all the operation. The computer can now perform all the operations. Now I could manually do everything at this point. But I would need to put every single operation into this by hand, by flipping the levers, and then, like I did now, say, hey, please write into A, please write into D. And that is not great. So instead, I want to be able to do all of that in an integrated way. And that is the next step. So I said I want to do everything in an integrated way, which means if I want to write to the A register, I want to tell the computer, hey, please write to the A register. How do I do this? So far, I have used this top lever to switch between A and C operations. I have used this is the lever that switches between RAM access or the A register, right? This is this here. This lever here zeros X, negates X, zeros Y, negates Y, F, and O for negating the output. And now I come to the bottom 6. This here toggles writing to A. When this is active, I am writing to A. Not merely by flipping the lever, but when I flip the lever, then it will write into A. And the logic of that is it goes down here. And yeah, this is a bit of a weird one, but writing into A is super complicated. It goes into here, it goes into here. Activate write to A register if A operation or C with D1. So if I'm doing an A operation, I also always want to write into A. By default, the A operation always writes into A. I did it manually before, but whenever the A operation is performed, I'm writing always into the A register. I'm never writing into the D register. Okay, now this one is off. This one is on. This here is the writing to M register operation, and this one is the write to D register operation. So write to D register, I already showed, is just, I can freecam through here, is sending a pulse here, right? This pulse to write to D, this pulse to write to A, and the load pulse all the way back here, the green line, the load pulse to write into the memory wherever I want to write to, whatever is at rest. So now I only write to A, so only this top one is active. These bottom ones are not active. Yeah, and now the second this gets a pulse, and this magenta line is the main thing, like this is the actual main control of the computer. This is the clock. It's an ether hopper clock on a quite long cycle, to be honest, with 18 items in there for this, and I think for the other one I need more. But this ether hopper clock will now do things every few seconds whenever this moves over twice, so like a bit over 10 seconds. Again, this computer is very slow. Real computer has a clock speed of gigahertz. This has a clock speed of 0.1 and less hertz. But it will send a pulse here, and that pulse will very quickly, I can also do it manually with this button, extend this piston, and this piston extending means, hey, by the way, I want to, this is the same, right? This is the same as this button did. I want to load write to A. And if I'm changing things, like saying, hey, by the way, I don't want to write to A, I want to write to M, I am activating the middle one. So then when I send the pulse here, it will send this one to write to M instead. This here is a bit special. I don't want to write to M and D for an A operation. So whenever I have an A operation performed, I don't want to write. And I already noticed a bug in here that hasn't come up with any of my coding because I never did that. But currently it's not possible to write to A at the same time as writing to M and or D. Because what I'm doing is when this is active, I'm extending these pistons. So when the pulse comes around, this piston here cannot extend because this one already takes up the space. So I'm preventing it from writing, which is good because the A operation will use the same lines that the C operation uses. So if I want to code a certain number into the registers, like the 5 I did before, well, 5 is not an issue, but if I want to have an 8 in there, then this line would be active, and this is the same line that is used for writing into the D register. So I would be performing two operations at once, which I absolutely don't want. So that's why I'm blocking it. The reason this is wrong is that it also toggles when I'm performing a C operation where I'm writing to A, which is not correct. That is not the logic I want. This one here, this line should connect to here independently of that line. Yeah, again, it didn't really matter for actual coding because that's not a thing I never wanted to do, and you probably never want to do. Like writing to M and A at the same time seems completely wrong. I don't think you ever want to do that. Writing to A and D at the same time, M and D at the same time might be a thing you want to do. So this is writing, right? These are these three levers which tell the instruction write to A, write to M, write to D. Each of them independently, except A and any of the others don't work at the same time because of something I did wrong. There are three more, and that is J1, J2, and J3. And now I can finally get to these purple lines up here. These purple lines have two signals. One is negative. A number is negative whenever this top one, which is the last bit, is active. The other is hard to describe what this means. It means I'm doing an OR gate. Like this is just a redstone ladder which acts as an OR gate between the first 15 bits. So this one here is active if any of the first 15 bits is active, which means it's not zero. This sort of means non-zero, but it doesn't really mean non-zero. This is only non-zero if this one is also zero. If this one is active, but none of the others are active, that's just a large negative number. That's not non-zero. So the actual logic of whether or not it's non-zero is performed all the way back here. This is compact, but it's the same ideas, it's the same gates. This is just actual non-zero, which is, yeah, it's just combining these two signals into one. Here, this is the zero, equals zero, I mean. The non-zero is the other one. The equals zero is just combining these signals into one. If both are zero, then it's zero. This is not super readable, what I built here, but then I have the non-zero gate here, which again, it's just the logic of non-zero meaning I don't want either of them. I don't want the zero signal to be true, so it's sort of the inverse of that. So that is the zero because this is non-zero. This is a very bad explanation. It doesn't matter. The outcome is that I'm getting three signals here. I'm getting this one, which is that it's less than zero. So it's less than zero if it's negative, obviously. So this is just a negative signal. And this is inverted because it's this is a NAND gate. So I have the less than zero one, I have the equal zero one, and I have the last one, which is this, which is the larger than zero condition. And if in any of these three cases, I can set a toggle for whether or not I want to perform a jump. And a jump means I'm jumping to a different line in my instruction set. And this is my instruction set. It is the same block from over there. Technically, it could be a lot simpler because I don't need to load this. I don't need to write to this. I could set all of these copper bulbs manually because these are not modified during the execution at all. It just starts here. And by default, it just moves through the lines and reads all of these as instructions into these blue lines, doing all the things these lines do that I've shown. But in practice, it is useful for me to be able to sit here and code the thing and say, hey, this is the instruction I want. And then I have the load key, and then that instruction is loaded into the instruction set for the specific thing I want it to be. if the instructions here at the bottom say jump less than 0, for example, right? This one here is jump less than 0. Then if the condition less than 0 is met, so this purple line here, if this is met, then this will turn on, and then I am jumping. So if any of these three conditions are both met and the jump toggle is on, then I'm jumping. And if I'm jumping, at the next step, I am not moving to the next instruction by just going to the next tower. I am moving to the instruction at the position of my A register, another thing the A register does. So I'm performing an operation, like I'm calculating 5 minus 2. And then I'm checking if 5 minus 2 is negative. And if it's negative, then I'm jumping. This would be a valid instruction. And where am I jumping to? I'm jumping to the A register. And this is what I'm doing here. This is the A register line taken off into this thing. And this is just a, I don't only have a limited instruction set for jumping as well, because this is not super large. But if I send the jump signal, these become active. And now the jump positions are fed into this machine here. And this machine is the last thing I built. This was my final creation. This is, I'm actually quite happy with this. This is my counter. It starts off at, this is the reset button, it starts off at 0. And normally when I'm performing an operation, and now I'll use carpet mod to make this more usable, to be able to, I'm using button as a player to press the button. I am now performing a clock cycle. So I'm saying, hey, button, press the button. And I'm now incrementing this by 1. So it first took the instruction from position 0, now it incremented, and now it's reading the next instruction, position 1. And it's performing that operation, and now it's reading from the next instruction. And from the next, because this machine here increments. I am sending the increment signal here on this magenta line still. It can also increment manually, I suppose. And this is, I'm really happy with this, I must say. I'm quite proud of this. This is very similar to this thing I came up with many years ago, just way better and way more compact because it uses the wax copper bulbs. The one thing I ever really did come up with Redstone, I'm redoing, because what this is doing is, now I'm at position like 5. So obviously in the next step I want to move to position 6. And now I'm sending the signal, it will go into this, which will turn off this lamp, which is correct. But it will also go into this, which will turn on this lamp, which is correct. But it won't go any further, which is also correct. And now it won't even go to the second, because I'm only allowing it to go to the next if the lamp is already active, because that is when the next signal should go further. So now that I'm in position 7, I want all of these to turn off and the 8 lamp to turn on. And that is exactly what's happening. So this is the incrementer that I'm using to count which position of the code I'm in. But it's a bit more complicated than that. So this is just reading the signal, sending the signal into here, and if the signal is 0, block it from going further. I also need to be able to reset these and completely overwrite them, because if I'm jumping to the coordinates that I want to jump to. So I can manually now say, hey, please jump. So I'm sending the jump condition. The jump condition blocks the incrementer. Now if button presses button, it no longer can go through here. and this incrementer does nothing. Instead, what is happening, or is it happening? Oh yeah, instead what is happening is this piston here will extend, and now the jump signal is on. It will send the jump signal, and that jump signal will allow the jump coordinates from here, which are just the A register, to go down here. So first the jump signal arrives, which is the reset button. It will reset the memory of where I am, and then with a bit of a delay, this is what these repeaters do, just a bit of a delay, the positions in these copper bulbs will get overwritten. So in that sense, it works exactly like the RAM tower, only that it's horizontal again, which in this case does make it nicer. So I can now have player button use, it resets, and it reads the positions that were in the A register. And that is now my position. And now if I'm saying, okay, for the next step I don't have a jump, oops, this was quite a violent way to not have a jump. For the next one I don't have a jump, I am incrementing again. And that really is it. That is the machine. That is all the components. There's nothing more to it on the hardware side. This is what I did over the course of just under 2 weeks. And then on the last 2 days, I did some coding and wrote a program for multiplication and a program which is my masterpiece, I will say, for factorization, for finding out the factors, the prime numbers that make up any given integer. Those are the 2 programs I wrote, and those are my masterpieces. That I won't showcase now, because now I'm going to bed, but tomorrow I will showcase that. Alright, so I've showed off how most of the hardware of this computer here works. Again, this clock is what will activate every so and so many seconds, and it will send a pulse here, and this pulse does a couple of things. One of them is it sends the pulse to write to registers, and the other is it sends the pulse to either increment the counter to the next instruction or to jump to a specific instruction if the jump condition is met. So what I now need to do is, if I want to run a more complex program, I need to code into this block, which has space for 64 instructions. I need to code into this each instruction line by line. And the way I do this is I decide what instruction I want in the 0th slot. So this reads 0. And I manually set the load pulse by pressing this button. And then I click this one to increment the counter to the next. And then I switch all these levers around until it's the command I want. Press load, press increment. So much for that. But what does that actually mean? What commands do I want? So here I have more from the book and the screenshot. So this is sort of the overview. This is explained multiple times, but this is sort of the overview of how things work. And there are 2 instructions, as I said last time. One can write a value into the A register, the A instruction, which is specified by this first, and my mouse here, this first 0 being a 0, this first bit being a 0, and then all of these are just a single binary encoded number, and that is written into the A register. So that's pretty simple. The other instruction, the C instruction, is far more complicated. These first 3 bits are 1, although 2 and 3 do nothing. These do not matter. Then the next one is toggling memory access. If this is off, I am using the A register to input into the arithmetic logic unit. If this is on, I am inputting the memory value at the location that is in the A register into the arithmetic logic unit. Then there are the 6 toggles that I showed off, 4 that manipulate the input, 2 that manipulate the output. The 3 destination toggles, which decide whether to write to A, M, and or D, and the 3 jump conditions. So if I now also show this, this is the, where do I have the actual window? I see it here in, 1 second, I need to rearrange my stuff. These jump conditions, here it is, so I can have the mouse. The destinations are just read to M, yes or no, D, yes or no, A, yes or no, and any combinations of those. Although I suppose the combinations with A do not work because I made a hardware error, which I discovered when making this video, but it didn't matter. I never wanted to do that anyway so far. The jump condition has multiple outcomes. If none of the 3 toggles are set, it means it doesn't matter if it's negative or positive or equals to 0, you never jump. So this is the default. If you do not want to jump, all of these are 0. And then you have certain conditions, just jump greater than. So only this 3rd one is active, which means I'm jumping only if it's larger, which means the outcome is bigger than 0 of the calculation. I can jump if it is equal to 0. I can jump if it's greater or equal to 0 by combining these 2. I can jump if it's less than 0. I can jump if it's not equal, so if it's either positive or negative. I can jump if it's less or equal than 0, and I can always jump. If I definitely know I want to jump, I just toggle all of these on, and it doesn't matter what the outcome of the calculation is, I always jump. So together these make up these instructions, which are 16 bits long and which I can put into my instruction set in the computer. And then here is this handy table which tells you which operation you are performing based on the certain bits. Now, a real computer, at a certain point, you would pass these things automatically. You would use some language that you as a human can understand and automatically translate that into machine code, i.e. just numbers of zeros and ones. I did not do that. I did everything by hand. And this is where I did it. The first program I ever wrote for this machine, I wrote on the back of a receipt. And I made a few mistakes when writing it, but really not many. It was simple enough that I could sort of just go with it. So I want to first explain this program and then showcase it in the actual machine. So it is a simple multiplication. As I said, multiplication is not hard. In the hardware, it's nowhere present. Like the machine cannot multiply by itself. But of course, a multiplication of a times b you can think of as a plus a plus a plus a, and you do that b times. Writing that in some code that looks like it would fit into a normal programming language, so I suppose this is Python here, I first set the answer to 0, and then while I have b's remaining, I'm always adding an a to it, and afterwards I'm subtracting 1 from b. So at a certain point my b is 0, which means I've added a b times, and then I've multiplied a times b. So this is a 4-line long program which multiplies. Unfortunately, these things do not work as machine code. This is high-level programming, and it's the only programming I've ever done, so I've never written assembly or machine code by hand until this project. And translating that into machine code was not trivial, but once I understood how things go, like the rhythm of what you need to do, then it really went quite well. Obviously, this is not optimized, and there are probably better ways to do things, but this is sort of the simple naive approach, I would say. So I have three variables. I have the answer, which I want to set to 0 to begin with, and then that add the a to. I have the a and the b. So I need 3 memory slots for that. Also, I need to put in an initial a in because I'm modifying the b. I suppose the a I'm not modifying, but when writing this, so you see this is 24 lines long, starting counting with 0, this 24 line long program needs to be able to, I need to be able to differentiate between the a variable, addressing the a variable, which means addressing the memory location where a is stored, and the number of a that I'm putting in the beginning. So I'm writing a in and b in to symbolize the actual numbers that I want to multiply. And this is the program. So I start out with this at ans, which means I'm performing an a operation, the first bit is 0, where I am addressing now the location I want to store the answer in. So this is not the value 0 I have in the beginning. This is, you see here, the value 8. So I arbitrarily decided to store it in memory location number 8. And now every time I'm addressing the answer again, I first need to address the memory location 8. So in line 16, this repeats at ans is the same command, which is just the number 8. I am then setting m to 0. So I am setting the location of the answer that I now have in the A register to 0. And then I'm writing into my A register the value, not the location, but the value of A, so the whatever I want to multiply, and that I'm then writing to the D register. And then I'm addressing the location of 8 and writing into the location of 8 the value that I had in the D register. So just setting a equals 5 in the beginning takes these 4 lines. And this is why the code becomes so long, because you need to juggle around which is in which register and that you're correctly addressing the correct memory. I'm now doing the same thing for B. Again, these 4 lines, the same thing for B. And for all of these, if I say I want to have D equals A, I'm just referencing this table to figure out what do I need to get the ALU to output A. And the answer is I want these bits set like that. So if I look at D equals A, the first 3 are 1 because it's a C operation. The last one is 0, the fourth one is 0 because I'm not addressing memory. Then the next 6 bits are what is in this table here. So 1, 1, 0, 0, 0, 0. And the next the next 3 are then where to store it, which is 0, meaning not storing in A, not storing in M, yes storing in D. And then jump condition, I don't want to jump here, so these are all 0. And this is my initialization phase. So I can now go into the actual machine, and I suppose I'll do it like this and keep this one up here. Yeah, that seems fine. All right, just go back into the actual world, and these towers now contain these instructions in this order. I'm using FreeCAM, that's maybe a bit easier. So the first instruction is just reading from top to bottom a 1 in the 4th to last location. All others are 0. So this is 0. Then 1 has a bit more. It has 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, and so on and so forth, all the way until line number 23. So this is 8, 16, and then 17, 18, 19, 20, 21, 22, 23, and 24, right? This is the 24th line, which now should have the command 1110. Let's check 1110. Then it's 1010, 1010, 1000, 0111. So I'm using up these first 3 rows of my 8 rows of available instructions just for having a simple multiplication. And if I now want to run this, of course, I need to first decide upon what do I actually want to multiply. So let's do maybe a simple multiplication, and let's multiply, let's say 3 times 3. So if I want to multiply 3 times 3, what I'm doing is I need to first set the a in to 3. Now a in is line number 2. So I need to go to line number 2, and I can manually change these bulbs, and I can read here what is currently written in line number 2. From this output, and apparently it is a rather large value. I don't remember running such a large multiplication because that seems like effort, but maybe the effort is probably not that high because the way this is written, it depends, the time this takes depends on how big b is. So I presume that what I'm multiplying here has a rather large a and a rather small b. So let's quickly double check that. Let's go to line number 6 and check what b in is. And here we have it. B in is just 5. So it is indeed a rather big times a rather small number, but for simplicity, let's just do, as I said, 3 times 3. So I now need to put in the number 3 instead of whatever this is, and I'm pressing load. Now you see the instruction changed to 3, and then I'm going back to the B register by going to location number 6. And I am changing that. Well, I'm not changing what I put in here, I'm also putting in the number 3. And the rest of the code is already in there, it's already correct. I can now reset the machine, go back to the beginning, and it will read the first instruction, which is again just addressing memory location 8. All right, this is me from the future. In editing this, I realized that so much went wrong in the original showcase that I cannot salvage it. I cannot possibly edit this together in a way that is coherent. Yeah, there were multiple bugs. Things that worked fine in my previous tests, but not when I tried to showcase it. Well, so I'm redoing it. This is the multiplication program. It is still calculating 3 by 3. I just checked, I just reset the machine, and I've installed this very lovely button helper character down there, so I can toggle clicking the button from up here and watch the machine work. And I will step through things line by line. The first step is to write the location of the result, so not the result, the location of the result into the A register, and that is 8. And if I go over here, this is the register, the memory location number 8. So now it's currently reading from location 8. And into that location 8, we want to write the number 0. It's already 0 right now, but it's still necessary to write a 0 into it because in general it might not be 0. So now it is definitely 0. So this is the first step. Why? We want the answer to start out being 0. Next step is writing the two numbers we want to multiply with each other into memory. So that starts by first writing the number into the A register. It's a 3. and then writing that from the A register into the D register. It is not possible to write it into the D register directly. It needs to go first into the A register and then into the D register. Now the A register can address, and now I'm in my own way, the A register can address the location of where we want to store 8, which is location number 9. So that's this tower back there. And now it will, there's the pulse, it will write a 3 into location number 9. So that was A. Now same things for B. Write the 3 into A. And in general, of course, this is not the same number, but here in this example it is. I don't know why I did 3 times 3 and not like 7 times 3. It doesn't matter. D equals A. So write the 3 into D. And then here you can always see the pistons changing when I'm switching between an A and a C operation. Like so. Now it will take the ALU value instead of the instruction value. And now the step is to actually write this into the location for B. And now begins the loop. So the first step is to just address the location of B. It's already currently addressed, but again, it needs to reset because in general it is not once we repeat the loop. So now at B is now correctly addressed. The next step is to write the value of D, of the D register, which is 3, still from before. Here I'm making use of the fact that it is still the value from before. Well, that's not true. I'm saying nonsense. We are writing into D the value of memory. So into D now we are writing a 3. So yeah, it's the same as before. This has already had the correct value in the first iteration, but that's just how the code works. And now this is the point where if D is 0, that means we have performed our multiplication. We have performed all 3 steps of a multiplication. We're multiplying A times B by saying A plus and so on plus A, and we multiply it B times, right? So if we now check if we have performed it B times by checking if B has been reduced to 0, and we set the location of the end of the loop into A, and now it's performing the jump operation. Or rather, it is not, because of course this is not actually 0. So the jump operation will now read this middle line here is now active. So if this middle line and the actual signal here were to turn off at the same time, now this has turned off, but the signal is still running, then this redstone torch would turn on, which would activate the jump condition. It is not the case. We are not jumping, so the next operation does absolutely nothing. And now, because we know we have not exited the loop, we need to perform an addition. So let's address the location of A. So now this is line number 14. Going on to 15 now, which is to read the value of D, of M into D, which again is a 3 because both numbers are the same. Maybe not the best example, but I didn't want to change it now. So let's address the answer. The answer, of course, right now is set to 0, but we are now incrementing the answer by A. So we're adding 3 to the answer. 3, the value in the ALU, is now being written into this ramp tower here, where right now it reads 0, perform the operation, and now it reads 3. So this is line number 17, M equals M plus D. Line number 18, addressing the B register. And now the operation is m equals m minus 1. And this is why it's so useful to have like +1, -1 operations already in the ALU. It's already coded in the ALU. I don't need to first write a 1 into the other register and then calculate things. No, it just works like this. And this is now 3 minus 1 equals 2. And we're writing that directly into the location of b. So this concludes one cycle. What do you do at the end of the cycle? You jump back to the beginning. So address the location of the beginning of the loop. And now we do want to jump. We always want to jump. The ALU reads 0, and all 3 jump conditions are active at once, meaning no matter what these signals say, we are always jumping. So the jump signal is on, which blocks the increment signal, and instead this is going to be reset all the way back to the beginning of the loop. And now we're at the beginning of the loop and the instructions repeat. And this is where I can stop going through it manually, because it will keep doing the same things until at some point the jump condition in line 13 is met. And by that point it will jump to the end and then always just repeat the last 2 lines. So I can activate the clock, and now it will perform all of this automatically without me having to manually have press the button. And maybe while this runs, to speed it up, I can use a tick sprint 1 day, and I can explain this, which is to say, now the game is running as fast as it can. And it is running that fast in order for me to save time, because otherwise I need to wait for the fact that every single clock operation takes absolutely forever. This is now a 6, so the second addition has already been performed. Waiting for the third addition, and now this reads 9, so all additions have now been performed. You can watch the machine work and all these lights flicker on and off, but once it realizes that all the operations have been performed, it will jump to the end, and the end is just iterating the same 2 lines over and over again, which is to put end into the position of where to jump to and then always jump. So this is this, right? It's always just repeating. This lamp turns on, it turns off. Nothing changes anymore, nothing happens anymore. We can read the answer, which reads 9. And now we figured out that 3 times 3 equals 9. And it only took like 2.5 hours or more. Actually, I don't need to guess, I can check. By this point, yeah, it will be like 2.5 hours. So that is the first program I wrote, and it works. After bug fixing. But it works. The program was not bugged. It was the machine. There's small details, mainly to how pistons behave. Like, it wasn't that my logic was wrong. It was that the game sometimes does things you don't want. So I needed to add like 1 delay step into this, because otherwise the pistons would sometimes just sort of deposit the block here, and that would break things. Small details, right? But this is just how implementation always works. And the next step is the factorization program, which is much more complicated, where I will use the old clips from a month ago to explain how it works. All right, factorization. Simple idea. I'm putting in a number and I want returned a list of all the prime numbers that are the factors of that number. How do I achieve that? And this problem is a bit more complicated than this multiplication thing. I did not want to do this on hand. So the first thing I did is I actually wrote a Python script which does it to just check that my logic makes sense and it's correct. And in my first iteration of this, I wrote it as an actual function for having a function that tries dividing numbers. Because of course, for factorization, I need to check if the number is divisible. And I'm only doing things with integers in the computer anyway, so this problem is perfect for that. So idea is I have two numbers, a and b, and I'm checking if I divide a by b, what is the result and is it actually divisible? I don't return the remainder because I don't care. I just care if the remainder is 0 or not. And if it is 0, I'm saying it's divisible. If it is not 0 by default, I'm saying it is not divisible. So I can do this and maybe quickly, like as a showcase, just try divisible of this and 3. And if I run this now, I will, of course, not see anything because I'm not actually outputting anything. And I will see that this is 448, but there is a remainder, so it is not divisible. And if I do 27 and 3 and run this, I see that it is 9 and it is in fact divisible. So that's what this function does. And this is the baseline that I need for my factorization problem. I need to be able to see if something is a factor. And then I'm basically just increasing my number. I'm starting off with 2 as the smallest prime, and then for every single integer, I'm checking if the number is divisible. Obviously, I know that all even numbers larger than 2 are not primes, so it is very inefficient to check if 4 is a prime factor, but that would be a more complicated program. So I went with the dumbest, simplest approach by just starting with 2 and then at each point checking if it's divisible. If it is divisible, append it to the results and use the answer as the new result, because obviously if I'm trying to figure out what the prime factors of, let's say, 27 are, then I want it, after I've noticed, oh, 3 is a factor, to only continue with the 9 as a remainder. And I want to repeat the 3 because, of course, the 3 could be in there multiple times. So if I run it like this, it will tell me, hey, by the way, the factors are 3, 3, and 3, right? And if I put in 2026, current year, it tells me, hey, it's 2 times 1013. And this just works, right? This would be a prime, fun. This would be 2 times 2 times 37 times 37 times 37. And obviously this simple Python script is rather fast compared to anything my Minecraft computer does. Python itself might not be the fastest programming language, but the computer itself is fast. The Minecraft computer is not. But this is really all I'm doing. So I have a concept of a program and it works. So now I need to put that into my machine format, so into my assembler code. And this I'm not going through step by step, but what I am going to focus on is the fact that this thing here is 83 lines long, and that's not good. I can maybe put it over here instead and show both, but it's not good that this is 83 lines long, for the simple reason that I only have 64 slots. And yeah, sure, this starts counting at 1. I have some comments in there. I have things like this loop, which is not an actual command, but in any case, it's too long. So what I did here is I actually had a divisible function. It is a function that I'm calling by putting in the values into the registers where the function expects them. And then I'm jumping to divisible to the beginning of the function. And by the end of the function, I am jumping back to where this was. And I assume this is how this is done. I don't know. I have never coded in assembly. This was just me looking at how the commands work and figuring out what it needs to do. This is certainly not optimal, but this I think would probably work. I don't know. I never tested it. This is too long. Fortunately, I managed to come up with a shorter way to do this, which just skips this entire function nonsense, which saves me a lot of hassle with addressing certain memory locations. And this is the actual proper implementation of this script in, it reads here 66, but if I remove all the things like these statements for loops and locations, less than 64 lines, and therefore it fits into my computer and I don't need to extend it, which of course I could have, but I didn't want to. And this works. It basically does what this script on the left does. It sets some input number at the very beginning, and then it just puts things into arrays initially, and one of these is that I have one array which keeps track of where to put the next output if it finds a new prime, because obviously I need to write this array, I need to put it into different slots in memory. So I have one initial point that I'm putting things into, and then it just increments the number it's checking. And for every single number, it is dividing. That's this divide loop here, which is the same as this multiplication, only that I'm subtracting instead of adding. And then by the end, I'm just checking if it is divisible. It is exactly divisible if there is no remainder, if a is 0. So if it is 0, then I am continuing. If it is not 0, meaning it is not divisible, I perform a jump not equals operation. So I'm jumping to not divisible if it is not 0. And all this does is it skips this entire block, which writes things into the result array. And it's basically this here. This is this block that I'm skipping. And if it is not divisible, then all I'm doing is I'm incrementing b by 1, and I'm jumping back to the beginning of the loop, and I'm repeating. So this program is the same as this one over here, only that this is not a function, but just part of this single loop. And this I took. So I then took this and manually again transferred this into zeros and ones, into machine code. So this block of zeros and ones, except for these statements to know where I am, this block of zeros and ones is what I then hand coded into the Minecraft machine. Took a bit, but I put all of that into the computer, and that block of zeros and ones should now, for any given input number, figure out prime factors. And that is this. Although it is now, again, over a month later, and this is actually not the same world. It is a different copy of the world. This is the most up-to-date version where I removed all the other things. As I explained, this was initially my Redstone testing world, which was pretty empty, but it had some things. And in order to increase performance, I deleted everything. And it did increase performance, but I found in my previous test that just running other things, probably OBS, results in an MSPT at idle of 1.8, when my tests, when I optimized things, had it at like half that or less. And that's an issue because MSPT is how long it takes to compute a tick, which determines how much you can speed up the game with a sprint command with carpet mod. So I have reset the machine, and I can now code a number into it, and that number is the one I am factorizing. So this number here is 154. And if I put 154 into the machine, and I really hope I didn't make a mistake in the binary decomposition, if I put 154 into the machine, that is the value that will be put into memory for the actual factorization. So it will try to find all the factors of 154. And I would start the machine. This takes a long time, so I will immediately start tick sprinting, because again, it takes a long time to run this. And while it's already running, I can explain a few things about why it takes a long time, and then skip forward or speed forwards towards the results. So right now it's running at a few hundred ticks per second, which is honestly not that good. I mean, it's still much, much faster than by default, but it's only so fast. So if I go down into this register here has the value put in. And that value, it now tries if that value is divisible by 2. And you can maybe think that dividing something by 2 in the way division works with this machine, same as multiplication, is it subtracts 2 every single time, and by the end it checks if there's a remainder or not. Of course, 154 is divisible by 2, and it takes forever because it needs to perform this entire loop of a couple operations as many times as 154 is divisible by 2 by, if that makes sense. Like the result of 154 divided by 2 is how many times I need to go through that loop with how the division works. And 154 is a somewhat large number and 2 is a pretty small number, so it takes a long time. After that is done, it will realize 2 is a prime factor, and it will write 2 in the first location of the output. Great. However, then 2 might be another prime factor, right? It might be 2 times 2, or 4 might be a factor of the number. In this case, it isn't, but of course, in general, I cannot possibly know that. And that means it needs to repeat the 2 and try again. This time it will be twice as fast because, well, we've already divided by 2, so it only needs to do 77 divided by 2, but it still takes a while. And then it figures out, oh, 2 is not actually a prime factor, let me try 3. And it will try 3 and will notice that's not a factor, and then it will try 4. Obviously 4 is not a prime number, it cannot possibly be a prime factor, it is an even number greater than 2. It is utterly ridiculous to even try if 4 is a number, and with any optimized sane program I wouldn't do that. But I can't optimize it further because that would require making the program longer. And if I make the program longer, I need a longer instruction memory, which I don't have without rebuilding or adding things, which I could do, but I wanted to write a program within the constraints of what I have right now. So this is where we are at. And as of now, this here, this bulb shows the number it's currently trying to divide by. And again, the game is running at much faster than the normal 20 ticks per second. It is running, depending on whether currently operations are performed or whether it's just waiting, a few times to 20 plus times faster than normal. But normal is a single operation takes like 10 plus seconds because of travel times, because of just needing to wait until the ALU is finished, until all signals have traveled everywhere. So the clock speed of this machine is god-awful. Certainly this could be improved with optimizations, but only to a certain extent. It is simply the reality of Minecraft that it will never be fast. So that is why I'm using the tick sprint. And now, actually, what is limiting the speed of the simulation is no longer Minecraft itself, but actually my own computer, how fast it can run Minecraft. So this operation, which is very simple, takes a long time because it needs to actually physically move pistons in the world in order to figure out if something is divisible by 2. So while this runs, I'd just like to showcase a bit the machine working. I absolutely love this. It is so cool. Just looking at it, I can't even tell you anymore what it's doing. Obviously, I built every single piece of it. I coded all the instructions it's performing. But once it's running, once the bugs are fixed, it just sort of does its thing. And that is the beauty, of course, of a computer. This level of abstraction where I no longer need to think about every single elementary operation because the hardware takes care of it and my code takes care of telling the hardware what to do, what to actually simulate. And I think that is absolutely brilliant. It is so nice to be able to see the machine work as a physical entity where pistons move, where redstone wires light up and shut down again. This is a computer, not just in the logical sense that it follows the logic of what a computer does, but it is a real computer. Yes, it is digital. Yes, it is simulated within a video game, but it is a real computer with real moving parts that actually performs all the necessary operations of the computer that is simulating it. Way more crude, way bigger, but that is how computers started. They were very crude. They were very big, not as big as this, but very big nonetheless. And it is just sort of nice to start to get a feeling for what it must have been like for the pioneers to build these machines and actually wire things up by hand and come up with architectures and structures, and you start to understand how programs used to work, that you just have not just digital code that you in some way write, you download a new software and then install it to your machine, but that you actually put a piece of hardware into the computer with the instructions of what operations the computer should perform. That is what I'm doing here. I have over there this big block, and that contains all the information. Yes, I coded it by hand because it's a bit more convenient, but if I wanted to make this smaller, if I wanted to optimize this, it would not use the same design as my RAM. It would be a bit simpler. It wouldn't have all the input wiring. I would just have the data there. I would just paste it in there, and then the machine could read the instruction. And I could cut it out and paste in a different instruction set, and then the machine could perform different instructions. And the physicality of it all, that I am actually to move in this 3D world and watch the computer work, just gives me an appreciation for it that I would not have had otherwise. This project does not make me an expert. It does not mean that now I fully understand how computers work. But it gave me a type of insight I could not possibly have gained if I hadn't done this myself. If I had just watched some video which explains basic concepts. Of course, I read a book that explains the concepts, but I rediscovered them myself. I tried doing it and then realized why it is necessary to do it as is specified. Because you start to realize, oh yeah, this is what you need to do if you want to achieve this thing. And that just actually gives me tremendous joy. This has been a great project. It took up a big part of my free time in January, and now that it's middle of March, I look back at that time spending on working on this computer very fondly. I wish it were just a little bit faster, because if it were a bit faster, you could actually do more with it. You could run more complex programs. You could think about adding input and output, things that are specified within the hardware specification. So this computer could do, I could add these things, but alas, it is not within the scope. I could build a display. It is possible with redstone lamps, but everything is so slow. It doesn't feel particularly rewarding to imagine running more complex things than this on it. So for me, this journey ends here. I don't plan on making version V2, V3, V4, where I keep improving and keep optimizing things. This was really an off-the-cuff idea, and it worked way better than I would have imagined. But yeah, this is probably, at least for the foreseeable future, the end of my journey into computer hardware. I just want to continue this for as long as it takes to get the first division done and the first prime factor into writing the first prime factor into my results array, and then I can leave it there and reuse the end of the footage of what I recorded over a month ago to show all the factors and that it does actually work, that it does not stop after the first. But I want to continue until it has finished the first. And then, as I said, I will end because it will take a long time for this to finish. And reuse my old footage. I want to say one more thing beforehand, and that is why this factorization. It's a bit of a joke. It is also a genuinely interesting problem that is that is just small enough to fit that I can just run with this machine. But it is also a bit of a joke. And it is a joke about quantum computers. The big idea is that in theory, a quantum computer could more efficiently factorize numbers, which is in general quite a computationally extensive problem, even if you do it smarter than this crude problem does. However, the use of Shor's algorithm on real, not simulated, but real quantum computers has never managed to factorize anything bigger than 21 as far as I'm aware. There is debate over whether that 21 counts or what exactly is the biggest number. 21 is the one I'm aware of, but someone will probably say that actually it failed to do 21 and it is 15. And then maybe it didn't even really do 15. Fact of the matter is it could not figure out that 154 factorizes into, well, the 2, let's say, is the easy part, but then the remainder, if you divide it by 2, and I will need to continue the sprint, the 2, once you have achieved that, you're left with 77. And of course, 77 is 7 times 11, which is a much bigger factorization operation than anything that has been achieved with real quantum computers. So the joke here being quantum computers are at a state of development where I, as a beginner, can build a computer in Minecraft that does it better. Which is not to say that I'm so brilliant. It is not difficult to factorize better than 21 on a computer. But still, the fact that following design specifications, of course, I was able to build a computer that performs better than a quantum computer. And one of the big topics people tout quantum computers as doing, yeah, I wanted to be able to say that. And that is why I chose this exact problem. So I will now stop the sprint and do the last few steps here at a reduced pace. I sort of already regret it because that means it takes forever. But this will go down to 0. And then it will figure out, hey, it's 0. And it will write results into the first of the result memories, which is this, which already reads 2 because I already ran this. In the same sense, this already reads 7, and this here already reads 11. So yeah, it did work. I already ran this. But I can maybe very briefly mess with it, like just to prove a point, that it will actually write the correct number in there, that it does actually overwrite what is in there. And while it does this, I can also have a look at the other registers. This here is the register number 8. Oh, now it performed the last subtraction, so it's 0. So now it will figure out that 0 is indeed equal to 0. This is register 8, which is where the first output will be stored, and then the second and third and so on. So in theory, I can factorize numbers as many as fit into here and as big as I can store in a 16-bit number, in theory. In practice, this first division would already take so long that it's not feasible anymore. But running this computer for an infinite amount of time, it would solve these problems. It would just take a long, long time. But it would solve the problem. So this is a general machine. I just want to reiterate that. I want to highlight that. I've selected multiplication and finding prime factors as things I can do that are simple enough that I can do them, but challenging enough that they're somewhat interesting. But this is a general computer, a general machine with higher clock speed and a bigger instruction memory. I could do basically anything a 16-bit computer can do. I do regret stopping the tick sprint, I must say. I will quickly maybe do tick rate 100, so not quite sprint. And here you see it sometimes fails to actually do 100. And the sprint just optimizes that it always does as many as possible. Now I just really hope it doesn't like break or anything. That would be quite annoying. And here we have it. It reset the memory and wrote a 2 into it. And now this here will decrement back down to 1, perfectly corded, and then it will increment back up to 2 because it's repeating the 2, and every single loop it will increment by 1. So in order to repeat the 2, it had to first decrement to 1 so that it can go back up to 2. So now it's back up to 2, and it will perform the same steps as before, only now it will put 77 into this, and then it will try it for 3, for 4, for 5, for 6, for 7, and for 7 it will realize, oh, it works, go back down to 7, won't work, 8, 9, 10, 11, it does work, oh, I'm done, and then the program will exit. So I will just briefly add the clip of that from back then. And that's it. That's the end. And I won't add any additional closing words. I've said all I have to say. So that is the computer I built in Minecraft.